All right, the last thing we're going to have a look at in our binomial distributions topic is the idea of sample proportions. So a population proportion P is the number of people or objects in the population that have a certain characteristic as a fraction of the total population. So if I surveyed 20 voters and 7 say they vote for the party WTP, this is a binomial experiment with 20 independent Brunelli stages. You either vote for them or you don't vote for them. And a random variable x of 21 possible values. 0 vote, 1 vote, 2 vote, 3 vote, all the way up to 20. Now I could write my result that there are 7 voters, or a proportion of voters is 7 on 20. So this binomial random variable x has 21 possible values, 0, 1, 2, 3, or 20, and the new random variable p hat also has 21 possible values. 0 on 20 voters, the proportion could be 1 on 20 voters, 2 on 20 voters, or 20 on 20 voters. Now this sample proportion p is the best estimate of a population proportion from a single sample. So, in other words, it's saying that we can get a sample of a large population and survey them and predict things about the whole population. And of course, the larger your sample, the more accurate this is getting. So the proportion that a certain amount of people follow this characteristic is going to be the number of people who follow that characteristic on the total number of people. And that's the proportion of people who follow a particular characteristic. Now, please don't think of this as a probability. Yes, it kind of is a probability, but if you get it in your idea that it's a probability, you're going to get confused, because later on we're going to look at the probability of proportions, and then if you get in your head you're looking at the probability of a probability, it's going to sound confusing. So think of it as a proportion, not a probability. Now, from the central limit theorem, for large sampling sizes, the distribution of something is approximately normal. So that's the central limit says if our sample size is large enough, anything is approximately normal. So a company produces batteries and does annual checks to see what proportion of them are defective. In the last 3 years, the number of defective batteries was sold as follows. Find the sample proportion of each of these years as a percentage. So in year 1, it's going to be 31 on 1,500, and that as a percentage is 2.07%, or to one decimal place, 2.1%. Year 2, we've got 19 on 1,100, which is, times by 100, 1.7%. And in year 3, it's 45 on 2,000, which is 2.3%. Now we're going to use these results to set the average percentage of defective batteries. Of course, all we have to do is do 2.1% plus 1.7% plus 2.3% divided by 3. If we do that, we get the average is 2.03%. Okay, the sample proportion, mean, and variance. A sample proportion random variable p is not a binomial variable x because its values are fractions between 0 and 1 rather than whole numbers between 0 and n. The probability of each value p hat equals x and n is actually equal to the value of x, the probability of x in the equation. Now this is because since each value of x represents a particular number for each certain parameter, such as getting 4 heads when tossing 6 coins, then each value of x could have its own probability calculating using a normal binomial distribution. So if we forget about proportions for a second, we can calculate probabilities using the binomial theorem. But to calculate a sample proportion, we're simply dividing this value by a set value of n. And the value of n that's used in the calculation of each one of these values of x is the same for each value. This value of n in this equation up here doesn't change. Which realistically means if we compare these proportions and their probabilities, nothing has happened to them because we've divided by the same value of n. If you did their ratios, that would be the same. So because we're dividing by the same value of n, that means their probabilities have not been affected. So the probability of each sample proportion, so the probability of the proportion, this is where you don't want to accidentally confuse yourself and say the probability of a probability, is just the same formula as the probability for a binomial random variable. Because of that, the variance and standard deviation are exactly the same, except since we're dividing by n in the formula, we're going to divide the mean, which was np, by n, the variance by n, and the standard deviation by n. So for a sample mean, it's the original mean divided by n, and the sample standard deviation is the original standard deviation divided by n. So find the mean, variance, and standard deviation of a sampling distribution of p is 0.4 and n is 50. Well, for a normal binomial random variable, it'd be 0.4 times 50, but we divide it by 50, which is 0.4, which confirms that formula that the mean is equal to the p. So, and we're going to do the standard deviation. So the standard deviation is the square root of npq. So n is 50, p is 0.4, q is 0.6, divided by 50. So 0.069. Next example, so the mean, well, it's just equal to 0.9. 0.9 times 125 divided by 125. The standard deviation is the square root of 0.9 times 0.1 times n. I've accidentally changed the order there, but it doesn't matter, on 125. Okay. Example 3, I've got a social media survey found that 134 out of 256 respondents had used some sort of social media within the past year. Calculate the expected value for the proportion of people who access social media. Well, the expected value is just equal to the probability of success. We've seen that. So the average is equal to p. That's our formula. And the probability of success is 134 on 265. Which is 0.367. And the standard deviation, the formula, is the square root of npq for a sample proportion on n. The square root, the sample size is 265. The probability of success is 0.367. The probability of failure is 1 minus 0.367, which is 0.633. Approximately. Over 265. Notice that these don't cancel in this case because there's a square root on the top. Which is at 0.0296. Okay. A coin is tossed 6 times. Let x be the binomial random variable and p hat be the corresponding sample proportion. Tabulate the probabilities of x and find the mean and variance. So what that means is, okay, x could either be x equaling x. Oh, no, x equaling x. You could either have 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, and 6 heads. And we're going to do some probabilities. So the probability that x equals x, I'm going to say that's x there. Well, I'm just going to do a couple of them. So this one's going to be 6 choose 0 times 1/2 to the power of 0 times 1/2 to the power of 6. Which is 1 on 64. I'm going to keep going, so 6 choose 1. 3 on 32. Notice that when it's 1/2, you don't actually ever need to, you can just do 1/2 to the power of 6 every single time. Now I'm going to leave the frequency polygon, as a famous textbook would say. It's going to be left as an exercise to the reader. Now we're going to look at p hat. Now p hat are just our proportions at 0, or the proportion of getting 1 head would be 1 on 6, and then 2 on 6, 3 on 6, 4 on 6, 5 on 6, and 6 on 6. And we've said that these probabilities are the same, and they are. So it's the same thing. Okay. Example number 5, what are we doing here? We're going to recall that a binomial distribution is discrete. So a binomial experiment with 20 Brunelli trials is being used to estimate the probability of p success in a Brunelli experiment. If the actual value p is 1/3, find the probability the experiment would yield an estimate with 0.05 of the actual value. Okay, so the actual value is 0.3, so p is 0.333 ... And we want to know 0.05 of that value, so p minus 0.05 is 0.283 ... and 0.05 above is at 0.3833 ... Now you might be thinking, okay, I need to choose actual values of p hat. Now p hat has to equal x on 20 because there's 20 Brunelli trials. Now 1 on 20 is 0.05. 5 on 20 is 0.25. So let's write this. 5 on 20 is 0.25. So 5 on 20 is pretty close to this value. 6 on 20 is 0.3. 7 on 20 is 0.35. 8 on 20 is 0.4. Now we can't choose random variables. We're not doing a normal approximation where we can look at long decimals. These are discrete. So we have to choose an actual value of x, 1, 2, 3, all the way through to 20, that's close to these proportions. Now we can't choose 5 because that means the proportion of 0.25 is out of our bounds, it's below it. So that we can choose 6 though. So we're going to look at the probability that our proportion, we're going to think, okay, we're going to choose p hat equals 6 on 20, or we're going to choose p hat 7 on 20 is 0.35, and 8 on 20 is 0.4, which is too big. So we're looking between x is 7 and x is 6. So really we're looking at the probability that x, we're looking at the probability that x, or that p hat is equal to, we're looking at the probability that p hat is equal to 6 on 20 plus the probability that p hat is equal to 7 on 20. Now remember, the probabilities of proportions are just equal to the probabilities of those individual values. So 20 choose 6 times by 1 on 2 to the power of 6 times 1 on 2 to the power of 14 plus 20 choose 7 times by 1 on 2 to the power of 7, 1 on 2 to the power of 13. And if you do that, you get 0.36425. So the probability that it's between 0.05 of the power value is approximately 0.36. Okay, the last concept in this whole topic is a normal approximation of the sample proportion of a binomial variable. So remember that for large sampling sizes, the distribution of anything is normal. So recall that if x belongs to a normal distribution of mean mu and variance sigma squared, and that for a sample proportion of a binomial random variable, the mean is p and the variance is pq on n, which means a sample proportion can be approximated to the normal distribution pq on n. So example number 6, and we're almost at the end. Example number 6 says a survey of 2,000 Australian voters is being used to estimate the probability that a random voter will vote towards the Working Together party. Assuming that the actual value of p is 1/3, use the normal approximation to the sample proportion distribution to find the probability that the experiment will use to estimate between 0.01 of the actual value. Now note here, continuity correction is not necessary as the values are very large. Remember, continuity corrections are only needed when we're approximating a binomial variable to a normal variable. Not in the previous one, because we weren't doing a normal approximation at all. Only when we're approximating a discrete variable to a continuous variable is that necessary. Okay. So the 2,000 sample is a sample of a larger population of all of Australia, and we don't need to change a value in x to fit the formula p hat is x on n like we did in the previous example, as a normal distribution is continuous. We can have decimals. So the proportion p is equal to 0.333 ... and we want 0.01 of the actual value. So we're going to go p minus 0.01. That gives us 1/3 minus 0.01. That gives us 0.323 ... and p plus 0.01 is 0.343. So we're actually looking at the probability that my proportion is between 0.323 and 0.343. Now, if this would be very tricky if we were not approximating it to a normal, because there's 2,000 voters. It would be ridiculous. So we're going to do some z-scores. We need to find the mean and the standard deviation. So the mean is simply equal to the probability of 1/3. And the standard deviation, do we know the standard deviation? It's equal to npq on n, which is equal to the square root of 2,000 times 1 on 3. Q would be 2 on 3 on 2,000. Which is 0.0105. So let's do z-score 1. It's going to be the value 0.323 minus the average of 0.333 ... over, we might be really accurate and write that as 1/3 over 0.0105. And if we do that, we get minus 0.984. And the second Z score is going to be 0.343 minus 1/3 over 0.0105. If you do that, you get 0.343. Is that right? 343. (0.9206). Okay, so really we're looking at the probability that Z is in between minus 0.984 and 0.9206. So if you do that, we're going to use our Z-score table to find the probability that Z is less than 0.9206 and minus the probability that Z is less than minus 0.984. And if you use your Z-score table, you're going to get 0.66. Okay, I think that's all I want to do. What have I got at the end? We might do this one at the end. So last example for this video, the incidence of asthma in a particular population is 21%. A sample of 89 people was taken. Part A, how many people in this sample would you expect to have asthma? Nice and easy, 21% times 89 is 18.69, so approximately 19 people. Part B, find this sample proportion as a fraction, 19 on 89, nice and easy. And part C, where it gets fun, assuming that the sample proportion is approximately normal, and that means the sample proportion is big enough, what is the probability that the proportion will be, percentage of people will be less than 10%? Okay, so what we want to know is, well, we're doing some Z scores here and we want less than 10%. So when we approximate a binomial variable to a normal distribution, we need to know its mean and standard deviation. So the mean is going to be 21%. So 21% of people have asthma, 0.21. And you could calculate that by going the probability of success, which is 21%, and the standard deviation is equal to the square root of NPQ on N, which is the square root of, how many people are there? 20. No, there's not, sorry, there's 89 people, ignore me. Wait, I feel like I've done something wrong. The standard deviation is PQ on N, not NPQ on N. Let me just quickly, let me backtrack, sorry. I thought it was, oh no, yeah, it is, NPQ on N. Okay, I'm silly. Ignore me, I was right the whole time. Okay, so 81, 89. Now 1 minus 0.21 is 0.79 on 89. And if we do that, we get 0.043. So that's our standard deviation, and our mean is 0.1. Now we want to know the probability that less than 10% of people have asthma. So we want to know, when is this proportion equal to 0.1? That's what we want to know. When is this proportion equal to 0.1 or less than 0.1? So we want the probability that P hat is less than 0.1. That's what we're trying to figure out. So to do that, we need to find a Z-score. So we're going to transform this into a Z-score question. So Z is equal to our goal 0.1 minus the mean of 0.21 over the standard deviation of 0.043. Which is minus 2.55. So we're really, ooh, let me fix that. Let's delete that. So we know that the z-score is minus 2.55. So we know the probability. We want to know the probability that z is less than minus 2.55. And if you use your z-score table, you get 0.0054. And I imagine we want a percentage, because the question was in lots of percentages. So 0.0054 times 100, 0.54%. What was that? What did we want to know? What percentage of people? What is the probability? Oh, okay, we just wanted probability. I guess so. Those two answers would be correct there. Now we want to know now more than 30%. So more than 30% is going to be the same as 1 minus the probability that the p-hat is less than 30% or less than 0.3. So let's do a normal z-score again. So z is equal to our goal of 0.3 minus the mean of 0.21 over the standard deviation of 0.04317. If we do that, you get 2.08. So we want now the probability of 1 minus p that z is less than 2.08, which is 1 minus on your z-score table. 0.9812, which is at 0.0188. And that's our answer. That's sample proportions. Thank you.